Hello everyone and welcome back to the Kohi Game Engine series. Today we're going to take a look at creating a geometry system. I would like to take a quick second and thank the supporters of the channel, beginning with our partners Eearslya, Wensheng, and Caden. They are the partners of the channel, which is the highest tier of support for the channel, so thank you very much for that. And I would also like to thank all the other supporters listed here on the screen. Your support is very much appreciated, so thank you for that. So, a geometry system. What do I mean? Well, let's get a couple quick definitions out of the way. First, when I'm talking about geometry, I'm talking about what we're going to be feeding to the GPU to render on the screen, right? All of our vertices and our indices, that type of data, right? We're going to wrap that up and package it up in something that we're going to refer to as geometry. And geometry is going to have a lot of uses in the system. One of those uses is going to be rendering, but we might also use geometry for things like collision and so forth down the road. But for now, we're just going to use it for rendering, okay? And so what we're going to do is we are going to make a geometry system to manage said geometry, manage the process of loading it and unloading it, and at least for now, uploading it to the GPU. We're definitely going to have other uses for it, but we'll cross that bridge when we come to it, okay? So, in this episode, we're going to create a geometry system that's going to operate a little bit similarly to our other systems, but there are going to be some key differences, right? However, before we jump into that, once again, there are a couple of quick things that we're going to need. So I want to go ahead and knock those out before we actually continue any further. So the first thing is going to be under KString. We are actually going to add one method to this, not a ton like we did last time, just one. And that is going to be a string empty function. And this is sort of just a convenience method, and all it's going to do is take the string that we pass it, make sure it exists, and then set the first character to 0, effectively making it an empty string. Okay. Now some would argue that this may be kind of pointless, but I kind of like not having to deal with raw string data all over the place, right? So here is the definition for that. Again, like I said before, we just check to see if the string exists. We set the very first character of it to 0, which essentially null terminates the string, and then we just return the string. Okay, nice and simple. One more thing I would like to do is under our systems, material system, there's one method that I would like to add to this, which is a method to get the system default. No, method to get the default material, right? We don't have that in here. So we just need a quick method to go ahead and get that. As you might expect, the definition for this is actually pretty straightforward. So right here above load material is where we're going to go ahead and put that. And all it does is check to see if we have a state pointer and returns the address of the default material. Otherwise, it throws a fatal error saying that we tried to get the system default texture before the system was initialized and returns a null pointer. Okay, so that is it for the material system. Okay, so before we can go any further, we also need to add a resource type for our geometry. So similar to the other resource types, we have a maximum name length. Again, we're going to go with 256 characters on this one. And then we also have a structure for geometry. So this has an ID, which is a unique identifier for that particular geometry. It has an internal ID, which it uses to map to the renderer specific internal data. It has a generation that will be tracked anytime the geometry is updated. It has a name, and it also has a pointer to a material. So a geometry basically glues together our vertex and index information along with a material, and both of those things are combined to then pass off to the renderer to be rendered, right? So it just makes sense to group those things together, okay? And so what we're going to do now is we are actually going to start implementing the system that manages these geometry objects, okay? So to get started with that, I'm actually going to go into our Vulkan renderer, right? So under renderer, Vulkan, I'm going to go to Vulkan types INL, and we're going to add our backend types here as well. So if we come down here, right about here, one thing I'm going to fix real quick is this is max number of objects. This should be material instances, right? Because that's how many we can have. Again, we still have a to-do to make this configurable. We're actually going to do pretty much the same thing for geometries right now. So we are going to have a maximum number of simultaneously uploaded geometries. And this is the maximum count that the backend can actually hold, okay? And again, we're going to have to do some work to make these things configurable, right? And actually, I want to add this to do here as well. So we're going to call that Vulkan max geometry count, and we're going to have a maximum of 4096 for right now. Again, we can expand on that later if need be. Next, we'll go ahead and define our structure for our internal data, which in this case is going to be our Vulkan geometry data. So obviously OpenGL and DirectX, when we get to those, will have their own types as well. So the first thing that this has is an ID, and this matches up to the internal ID that is on the geometry itself. We also have a generation here to keep track of if we need it. And then the other thing we have is some vertex information and some index information. So what we can actually wind up having here is a vertex count, which is the total number of vertices that are going to be included here. The size of the vertex buffer object, the vertex size that's going to be needed. So that is basically the size of a vertex times this count here, right? So this is the size in bytes. And then a vertex buffer offset. And this is actually how far into the buffer from the beginning this particular geometry data is stored, right? So we have a set of those for vertices, and then we have a set of those for indices. So one more thing before we're done is we need to come down here into our Vulkan context, right? And almost all the way to the bottom, right before our function pointer to find memory index, we are actually going to set up an internal array of geometries of the size of Vulkan max geometry count, which is that 4096. And you'll see here that I also have a to-do to make this dynamic, right? So eventually we will be making this dynamic, but for now, just to simplify things, it's a little easier to manage this way, okay? So now our context is going to hold those internal geometry data objects for us, okay? All right, so that is pretty much it for the Vulkan types, right? So we have our Vulkan types, we have our resource types. One other change that we're going to make is to our renderer types. So if we go to renderer types INL, we're actually going to change a couple things here. So we have here our geometry render data, which currently holds a model and a pointer to a material. This is no longer going to hold a pointer to a material. Instead, it is going to hold a pointer to geometry. And we're just going to call this geometry as well, okay? And the geometry, as you may recall, holds the material, right? So when we go to render a geometry, we need to know what geometry we're going to be rendering, and then the transform for that geometry, okay? And that transform can come from anywhere, which is why we just provide a model matrix. All right, so that is the first change that needs to be made. The next thing that I want to change is we have this update object here, which takes in geometry render data. The term update object doesn't actually make too much sense anymore. We're actually going to rename this to draw geometry, okay? And we're going to have to remap some things to make that fit, but I think the name draw geometry fits a lot better, I think. So we have that, and then as with our other systems, we're also going to need to be able to create and destroy geometry. So our create method is going to take a pointer to geometry that's going to be populated with some of the values, specifically our internal ID and a couple of other things. We're going to take a vertex count, an array of vertices, a index count and an array of indices, okay? And from this, we'll be able to go ahead and upload to the GPU in our backend. And then, of course, to destroy the geometry, all we really need is the geometry pointer itself, because it'll actually have all this information that it needs, including offsets and so forth. Okay? So, one more thing that we're going to have to change is our render packet. We're actually going to make use of our render packet now. And what we're going to do is we are going to pass through, in the render packet, sets of this geometry render data, right? So we're going to hold a variable here full of geometries, and then we're going to indicate how many geometries we're going to pass, right? And so this will allow us to take that geometry information out of the renderer, place it into the application, and then pass it to the renderer as it should have been all along, right? So we're finally removing some more of those hacks that have been in place, all right? So that is renderer types INL. So the first thing I'm going to do actually to start supporting this is I'm going to go to the Vulkan backend.h, and I'm going to change this Vulkan backend update object to draw geometry. And I'm going to go into the backend and make that same change. So we have change this to render draw geometry, right? And the other thing that I'm going to do is go back to the H file, and I'm going to add two new methods. Similar to our textures and our materials, we are also going to ask the renderer to create and destroy geometry for us. This handles, of course, the internal objects that we've already talked about. Okay, and for right now, I'll just go to the bottom of this file, and I will stub out these functions, and we're going to fill them out in a bit, right? I just kind of want to get everything sort of hooked up first, and then we can come back and fill this out. All right, so those are in place. So that means that our renderer backend.c needs to be filled out as well, okay? And so all we're going to do here is we're going to change update object in both places to draw geometry. We're going to change Vulkan backend update object to Vulkan renderer draw geometry. And then we're going to add our new two function pointers for our create and destroy geometry. And then likewise, we're going to come down here to the bottom and zero out those things in the destroy. Okay, so now those things are hooked up, and we can at least call these from the front end. Speaking of the front end, we need to actually go ahead and create these methods on the front end as well. So we'll go to renderer frontend.h. Right here at the bottom of the file, we will put renderer create geometry and renderer destroy geometry. All the parameters are the same. In renderer frontend.c, we're going to go to the bottom, and we're going to insert two new methods here, right? Our create geometry and our destroy geometry. And those just call the back-end versions of those things, okay? So that is that. So obviously there is still work to be done here, but we'll come back to that after we create the geometry system, okay? So with that said, let's go ahead and create our new system. So under systems, we're going to create a new file. We'll call this geometry system.h. Obviously, we'll start off with a pragma once and a include of the renderer types. And we're going to start off with a geometry system config. Again, this only has one property, which is max geometry count. We have a note here, though, that this is the max number of geometries that can be loaded at once, and that this number should be significantly greater than the number of static meshes. We'll come back to that, because there can and will be more than one of these per mesh. We should take other systems into account as well. So the number for this should be at least somewhat high, right? And so what do I mean by static mesh? Well, a static mesh is a collection of geometries, right? It can have one geometry, it can have multiple geometries. Typically, you'll have one geometry per material, right? And you can have a fairly complex static mesh that's made up of all these sort of sub-objects. And each one of those sub-objects would be a geometry, okay? And so because you can have multiple geometries within a static mesh, and you're going to wind up having, probably hundreds of static meshes in a scene, you need to be able to make sure that you have enough geometries available, or enough slots for geometry available to be able to handle that. Okay, so that's all that's talking about. We'll cover that more in detail when we actually get there. So the next thing that we're going to need is geometry config itself. This is not to be confused with the geometry system config. This is configuration for an actual piece of geometry itself. This would be loaded from file, for example, okay? And this has a vertex count and an array of vertices, and an index count and an array of indices. It has a name for the geometry itself, and then it also has a material name. And then this material name is used to do our string lookup in our material system to get a pointer to the material that will be used with the geometry. So you can kind of see how these pieces are going to come together. Next, we're going to define a default geometry name of just default, right? We may wind up changing that, but at least we have a token for it that we can use in code. Similar to our other systems, we have an initialize and a shutdown. I don't really think any further explanation is needed from here, so I'm going to go ahead and skip over that. However, our acquisition is going to be a little bit different for this system because we are not actually going to be retrieving things by name, at least not right off the bat, because I don't think we're going to need that. Instead, we're actually going to be doing it by ID, and I'll go into the reasons why we are going to use ID once we actually set up our static mesh system, which is, spoiler, there's one of those coming as well. But for right now, we are going to be able to acquire by ID, which basically says we already know the ID of an already loaded geometry, so let's go ahead and get a pointer to it. If we do not have an ID or do not have a pointer to a geometry, and we need to instead load one from configuration, we can also acquire from configuration, and we could pass a configuration object and then whether or not it should auto-release, right? So this is for acquiring new geometry. This is for acquiring existing geometry, okay? Next, we have a release, which is pretty self-explanatory. We will also have a quick method for a get default geometry, right? So it just obtains a pointer to some default geometry. And then we're actually going to have a method here that is more of a utility method that we're going to use to generate some test geometry, okay? And this method is geometry system generate plane config, right? So we generate a configuration for a plane geometry. And we could pass it the width and height, which is the overall width of and height of the plane, right? So it should be non-zero. If it's 0 in either direction, it's going to just replace that with 1. The segment count, which is basically how many splits the geometry should have in it. So if you want a plane with a 4x4 plane, for example, then you would have 4 in the X and 4 in the Y segment count. Or if you just want a single plane, you could just put 1 there. If you enter 0, it's going to use 0, okay? And we're also going to have a tile X and tile Y. This is going to be used when we generate the texture coordinates for the plane. And this indicates how many times the tile should texture across the X and Y axis respectively. Again, must be non-zero. If it is 0, it's going to replace it with 1. And then, of course, the name for the geometry and the name of the material to be used with it. And we return a configuration which can then be fed into our geometry system acquire from config, which is right here. Right, so we generate one of these guys to actually pass that. Okay. An important thing to note is the vertex and index arrays in this method are dynamically allocated and should be freed when we're done with the object. So that is important to know because otherwise we'll wind up with memory leaks. We probably will wind up readdressing how this works in the future to use an allocator instead, but for right now, this is how we're going to do it because it keeps things nice and simple. Okay, moving on, we'll go ahead and create our C file. And our C file includes what you might expect, right? So we have our geometry system H, the logger, memory, string. We include our material system and our renderer front end, okay? Next, we'll have to type def a structure for geometry references, again, like we've seen in other systems. So we have a reference count, we have the actual geometry itself, and whether or not it should be auto-released. Next, we'll need to define what the system state looks like. So we keep a copy of the config. We keep a default geometry here. And then we also keep an array of geometry references. Now note that we are not using the hash table for this because we're not doing name lookups. So if we want to add that functionality down the road, we certainly can. We just don't need it necessarily right now, okay? So next, obviously we have our state pointer, which is just a pointer to our geometry system state. We have a few private methods that we're going to set up. So we have a create default geometry, which just takes the state, create geometry, which takes the state, geometry config, and a pointer to the geometry that's going to be created. And then the destroy geometry just takes the state and then a pointer to the geometry to be destroyed, okay? So those internal, those are the methods that actually do all the work, okay? All right, so next I'm just going to sort of plop in the initialize in here because we've seen a lot of this before. So what we have here is our memory requirement generation here. So we have our struct requirement and the size of our array. That's all based off of configuration and the size of geometry and the system state. Those things are added together to give us our memory requirement. Again, if state is not passed, we just return true. If it is passed, then we go ahead and store off our pointer, save off our config, and then the array block we go ahead and assign, and then our register geometries we go ahead and assign to our array block, right? So we get our array block and then assign it here. And then we go ahead and invalidate all geometries in the array, which basically consists of setting the ID, internal ID, and generation all to invalid ID, okay? And then we'll call our internal create default geometry, right, to set that up. And if for some reason that fails, then we can't actually continue with the application, so we bleat about it and return false. Otherwise, we return true. Pretty straightforward stuff, I think, for our initialize, right? So next is a shutdown. So the interesting bit about geometry is because the geometry information is all loaded into a buffer that is managed by the Vulkan backend, there isn't actually anything to do here. So note nothing to do here, right? Because we're shutting this down, it doesn't really matter. We don't have to clean up any resources per se, right? Releasing things out of a buffer basically just means no longer referencing them and or adding them to a free list. So there's not really anything there to be done, right? So next, we have our acquire by ID, which is actually pretty straightforward. So the first thing we do is we check to make sure that we did not pass invalid ID. And then we also check to see if the registered geometries sub ID, geometry ID, is not invalid ID, right? Because if either of those two things are true, then we need to throw an error about it saying, hey, we don't have valid geometry here, so we're not going to return anything. If all of that is valid, then it goes ahead and bumps up the reference count by 1 and then returns a pointer to that geometry. So pretty straightforward stuff. Next, we have our geometry system acquire from config. So all this does is basically loops through our geometry array, checks for a slot that has geometry ID equal to invalid ID, which means it's an empty slot and available for us to use. We set the auto release to the one that is passed in, right? So true or false. We set the reference count to 1 because this is a brand new geometry. So we have a single reference to it. And we go ahead and set our local pointer here to the address of that geometry. We also set the ID of that geometry to the index that we're at, okay? Finally, we get down here past the loop and we just do a sanity check to make sure that we actually assign something to this geometry here. So if for some reason we got to the end of that loop and did not, then that means that every single slot is occupied and we need to throw an error about that, saying we can't load any more geometries and boot out. Next, we call our private create geometry, passing the state pointer, config, and the pointer to the geometry that we've obtained here. And if for some reason that fails, we're going to bleat about it and return 0. Otherwise, we are going to return that pointer. Okay. So again, Pretty straightforward stuff. Geometry release is actually pretty straightforward as well. So the way that this works is it basically just checks that the geometry that's passed in exists. In fact, this should actually say geometry and geometry ID. All right, so we check to make sure that exists and then check to make sure its ID is actually valid. We go ahead and obtain a pointer to the registered geometry's sub-geometry ID. And then we go ahead and just for, because we're actually releasing this, we need to take a copy of the ID, because in a second down here when we get to destroy geometry, the geometry ID gets unset, right? So we first check to say if the reference count is greater than 0, then we go ahead and decrement it. And then down here, if the reference count is less than 1 and the reference auto release was set to true, then we go ahead and destroy the geometry itself. We set the reference count to 0 and auto release back to false. And the destroy geometry, of course, will reset the IDs, generations, and so forth. Okay. Otherwise, if the geometry IDs mismatch, then something has gone horribly wrong, right? And we actually are going to throw a fatal error, because this should basically never happen. If our IDs do not match for some reason, then something has gone wrong in our registration logic, and we need to investigate it. So we're really going to complain about it here and just abort. And so next, for some reason I actually had this line down here, and this actually is not needed, so ignore that. What we're going to do here is actually, instead of returning right here, I'm going to move this down here. So that way, if we hit this if block at all, that means we're doing something, right? And no matter what, we're going to boot out of it. Otherwise, if we don't boot out of here, then we're going to get a warning saying that we cannot unload, or let's say release, invalid geometry ID, right? So that means nothing was done. That's the kind of stuff that happens when you copy and paste, folks. So sometimes it gets you into trouble. But anyways, this should be correct now, okay? So that is our geometry system release. Again, it's pretty straightforward stuff, as is the next function, where we get our default. So again, if we have a state pointer, we just return the address of our geometry, or default geometry rather. Otherwise, we throw a fatal error saying this was called before the system was initialized, and we return null. Okay. Now, onto our private methods. So these are actually pretty straightforward as well. So our create geometry, again, takes in our state, our configuration to create from, and then a pointer to the geometry itself. So the first thing that it does is it sends the geometry off to the renderer to be uploaded to the GPU. So what we send off here is a pointer to the geometry itself, the vertex count, the vertices array, index count, and the indices array. Okay. And the renderer goes ahead and sets up all the resources that it needs behind the scenes to get this transferred to the GPU, right? So we're going to revisit that and implement the back end to that. All right, so if for some reason that process fails, then we're going to go ahead and invalidate the entry just by setting the reference count to 0, setting auto release to false, resetting the IDs. We should probably render create geometry. If that fails, that's actually going to throw an error message, so we're not going to bother throwing another one. We're just going to return false. Okay. If that succeeds, then we're going to go ahead and acquire the material if the config material name actually has a string, right? So if the length of that string is greater than 0, then we're going to go ahead and use that config material name to acquire a material by name. If for some reason that material is not acquired, say we get an error or something causes us to get a null pointer here, we're just going to check that and use the default material instead. Okay, so that way we have a fallback. We're not crashing the application in that case. And then we're going to go ahead and return true. All right, destroy geometry is next. So destroy geometry is pretty straightforward actually. We just call renderer destroy geometry. We reset the IDs. We empty the geometry name string. So we also release the material if the material exists and we have a name that is longer than 0, right? So we don't have an empty string. We go ahead and call material system release, passing along that name. And we go ahead and set the material to null. Okay, and that is all there is to destroying geometry. All right, so our create default geometry is actually lifted almost exactly from our renderer front-end code that we were using to generate that initial plane, right? And so we just create a small array, we zero it out, we set our positions and text chords and our indices, and then we go ahead and call renderer create geometry and go ahead and assign the default material to that and return true. Okay, so this is all basically lifted directly from the front-end code, right? There are some minor tweaks in here, but more or less this is the code that you need to use. Okay. All right, and finally we have a little bit of a more complex function. It's kind of long, but it doesn't actually do a whole lot, right? So most of it is actually just sanity checking, right? And this is our geometry system generate plane config, right? So we take a width, height, x segment count, y segment count, tile x, tile y, name, and material name. We check width and height to make sure that they are non-zero. If they are 0, we go ahead and assign those to 1. If the x segment count or y segment count are less than 1, we go ahead and set them to 1. And then we check tile x and tile y to see that they're non-zero. If they are 0, then we use 1.0 instead, which is sort of a default mapping, meaning repeat the texture once. Okay. Next, we go ahead and start creating our config. So we set the vertex count to the x segment count times the y segment count times 4. So this is 4 vertices per segment. On that note, this is something that should not really be considered production code. This is more of something to play around and test with. This is not something that you'd probably want to use in production, simply because A, there are dynamic allocations here, and B, all the indices and vertices are actually duplicated, right? We don't actually deduplicate anything here. We might add deduplication later, but for right now we're not doing that. We just want to keep this simple, right? So we set our vertex count to basically x segment count times y times 4, and then our index count is x times y times 6, right? Because we have 6 indices per segment. And then we obviously have our array that is set to those appropriate sizes for the vertex count and the index count, okay? So once we've done that, we go ahead and calculate the segment width, which is basically the width divided by the segment count. That tells us how much of the total width each segment actually is in 3D space. Okay, we do the same thing for height. Then we go ahead and grab the half values of those, and actually one thing here that I should note is we can make this a little bit more efficient by multiplying this by 0.5 f, right, instead of doing a division there. So we can go ahead and tweak that and get that fixed. Okay, and then we go ahead and we loop through the y. So we go, we iterate rows, and then we iterate columns, okay? And we generate vertices. And this is the min x and the min y. So this is the left, and you can think of this as the top. The max x is considered the right. The max y is considered the left, okay? And it basically just runs this logic here to create center geometry based on how many segments you have. For each segment, okay? And so we generate our x and y positions for the segment here. We generate our UVs here, which takes in the tiling into account, right? So there's an algorithm here for that. And then we go ahead and we calculate the vertex offset, which is going to be the vertex offset for this particular segment, right? And so we get that by saying y times the x segment count, which gives us an entire row, right? So if y is 0 and we have a 4 by 4, that number is going to be 0. And then it'll be plus the x, right? And that'll let us know how far into the array we actually need to be, right? And then we multiply that by 4 because we have 4 vertices per segment, okay? And so the next thing we do is we grab some pointers to each one of the vertices. So we take that v offset, and the first one is going to just be the v offset itself, so we add 0 to that. The second one is going to be the vertex after. The third will be the vertex after that, and the fourth will be the vertex after that. So we just grab pointers to those for convenience. And then we go ahead and we set the position and texture coordinates, right? And if we actually go back up here to this method right here, I kind of put in comments here how these triangles are actually generated. So our first vertex is here, our second vertex is here, and our third vertex is here. So that's one triangle in this direction, right? And then our first vertex of the second triangle, going by the index here, is here, then this one, and then this one, right? So we go this way, right? And so we're actually going to wind up doing the same thing all the way down, right? So instead of using hard code values, we just use our min and maxes here, right? So our min and max x and y, and our min and max for our uvx and uvy, okay? So we just fill those out, and then we generate the indices. And the way that we do this is we take an index offset to give us our position in the array, and then we use our vertex offset to indicate what these numbers should be. So in other words, if we look at, again, up here, our example, each one of these squares is rendered by doing 0, 1, 2, 0, 3, 1. And you'll note that we have the same pattern here, 0, 1, 2, 0, 3, 1, right? And so that is how that is done. So we just do that for every segment, and then once we're done with that, all of the vertices and indices will be filled out. Next, we go ahead and check the name and make sure that the name length is greater than 0. If it is, we go ahead and assign the name, copy that into the config name. Otherwise, we copy in the default geometry name into the config name, which is just default. And we'll do the same for the material name. And that is it for our geometry system. There's not a whole heck of a lot to it. I tried to blaze through that as fast as possible, so you know, most of this stuff is stuff that you guys have already seen, so I don't feel the need to spend a lot of time on it. Okay, so now that we have our geometry system, we need to actually change up some things in our material shader first before we actually jump into the Vulkan backend, right? So one of the things that I want to do is go here into shaders and open up the H file. And we have this other method here that its name is kind of poopy too, right? So we have this Vulkan material shader update object, and then it takes context, shader, and the geometry render data. We are actually going to split this into 2 calls instead. And instead of using the geometry data, we're going to handle this a little bit differently. So I'm going to go ahead and nuke this and replace it with 2 calls that we're going to split. First thing we're going to do is we're going to set the model, right? So we take the context shader and just the model matrix, right? And that, if you recall, goes to our push constant. So we're going to go ahead and split that out as a separate step because we may not have to do that every single time, especially if we're batch rendering or something, right? We want the flexibility to be able to do that as a separate step. Next, we have Vulkan material shader apply material. And this is more or less doing what the update object would do, right? So this takes the context shader and a pointer to the material that is going to be used, right? So since it's a material shader, it makes sense that we should be feeding material data to the shader, okay? Okay, so those are those 2 changes there. We have a couple of changes on the C file to make just to accommodate that. So I'm actually going to go down here to where all these errors are because this is the section that we need to change. So the first thing that I'm going to do is I'm going to go ahead and just bump in here Vulkan material shader set model, right? And this is taking the same push constant code that's here and it's just moved it up here, and instead of pointing to data.model, it's just passing the address of model, right? And so this is all one step now. So it just checks to make sure that the context and shader exist, goes ahead and gets the image index, the command buffer at that index, and then calls vk command push constants. And that's all that one does for now, okay? Which means we can actually get rid of that because we no longer need that, okay? While we're at it, we're going to change the signature of this, right, to apply material, okay? And now we're going to be able to reference this properly from the renderer backend, okay? So to accommodate the change in parameter, there's just a couple of small tweaks that we need to go ahead and make. The first thing that I'm going to do, though, is add a safety check, which actually wasn't here before, to just check if context and shader exist. So I'm going to open that there, come all the way down here to the very end, and close it there. So that way, just in case for some reason that doesn't exist, we actually have a little bit of a safety net there, and this just won't do anything, okay? So the next somewhat minor tweak is going to be where we are grabbing this data.material internal ID. We can just delete the data dot portion of that, and we're going to have to do that a couple of times down here. So we delete it here as well, and then we'll go ahead and delete it here as well, because that's the material diffuse color, and here as well, UBO generation, and once more here where we're saving off the generation, and once here for checking the texture, and I believe that is it for that method. Also, I'd like to fix a small thing in here. So we have our acquire resources, but in our release resources, we actually need to do a step before we call free descriptor sets, because there is the potential that this descriptor set that's being freed is currently in use by a command buffer. So we're going to call vk device wait idle to wait for any pending operations using the descriptor set to finish first. That'll keep us from getting potential validation errors when we go to actually release resources, okay? Just a small bug fix there. Okay, so that is it for the material shader, okay? The next set of changes is going to be in the Vulkan backend. So we are basically going to work from the top of the file all the way down to make all of our changes, okay? And the first set of changes that we're going to need is to our upload data range, right? And all we want to do is add a const to this, and that will be apparent as to why we need to do that later, but I just wanted to get that in there. We are also, since we have a upload data range, I also want to stub out a placeholder here for free data range, okay? And we have a to-do here to actually free this in the buffer and update a free list, which we also don't have. These free lists keep popping up, so I think we're going to wind up actually implementing that sometime soon. But for right now, we're just going to stub this out and have it in place, so that way when we do implement a free list, we don't have to worry about this as well. Okay, so that is that. Next, we are going to proceed to the section of code where we are generating our temporary test code. And finally, we can resolve this to-do, and we can actually get rid of all of that code, right? We don't need it anymore. And instead, after create buffers, all we need to do is loop through our geometries and set all the IDs to invalid ID, right? So we're just going to mark all the geometries as invalid, okay? And that's all we need to do here for now. Okay? So the next thing we're going to do is we're actually going to take this draw geometry and we're going to move it, right? Because I want to kind of place all the geometry functions together. So we're going to go all the way to the bottom of the file and place it after destroy. Okay, and we are going to make some changes here, but all the rest of the changes that we're going to make are going to be here grouped together at the bottom of the file. Okay, so the first order of business is to create the geometry, and this is quite a lot of logic, but I'm still going to paste it all in one piece because it just makes a little bit more sense to explain it this way. So the first thing that we're going to do is we are going to check our vertex count and our vertices to make sure that both exist. If one or the other does not exist, it's just going to bleed about the fact that it requires both and return false, meaning it failed to load. We are also going to check to see if this is a re-upload by looking at the current internal ID, and if it is not set to invalid ID, we're going to consider that a re-upload of the geometry. And the reason for that is we'll actually need to take a copy of the old range for use with our free list later on. And so I want to sort of stub out that logic now. Next, we're going to create a local pointer for internal data, right? And we're just going to start off by setting that to 0. And first and foremost, if we have determined that this is a re-upload, then the internal data is going to be set to the context geometries and then the geometry internal ID, okay? And after that's set, we go ahead and take a copy of the old range. Otherwise, we're going to search for a new entry, and once we actually find one, we'll go ahead and set the internal ID to that index. We'll go ahead and set the geometry ID at that index to I. Then we'll go ahead and set the internal data pointer to be the address of context geometry sub I. Okay, and then we'll break out of that loop, right? So we're either going to already have a geometry already ready to go if it's re-upload, or we're going to search for a new one and use it. Okay, here's a sanity check to make sure that we've actually assigned one. If it doesn't, it bleats and goes ahead and kicks out. We go ahead and save off a pool and queue variable just to kind of shorten our code a little bit, because some of these methods actually get kind of long. And first, we go ahead and handle our vertex data, right? So our internal data vertex buffer offset is the context geometry vertex offset. So that is the current offset that gets incremented by the size every time we upload, right? You'll see that here in a second. So it starts off as 0, which is the beginning of the buffer, and then we actually wind up incrementing it by this vertex size here. So next we copy over the vertex count and then get the size here, which is the size of a vertex times the vertex count, right? We go ahead and we upload that data range. So we call our upload data range passing context pool. I believe this is, yeah, we don't need a fence. We want to go ahead and use the queue that we saved off. And then of course we want to go into the vertex buffer. We want to use the vertex buffer offset that we assigned here. Here is the vertex size, and here are the vertices themselves. Now, you'll recall that in upload data range, we added this constant qualifier here. And that is because in this function, we have a constant here. And in the renderer function that this then calls, there is a constant there as well. So it makes sense that there should be a constant qualifier here as well. So those things are constant all the way through. And then we have a to-do here that we should maintain a free list instead of doing this, but for now we're just going to increment the geometry vertex offset by the size of the vertex size, right? Which again is how many vertices we have times the size of vertex 3D. Okay, so that's the vertex data. The index data is pretty similar, only it checks first to see if we actually have an index count and an indices array, because it is possible for us to have geometry that does not have index data. And so we should be able to handle that. And so this only happens if we actually have data for that, okay? If we do, we go ahead and calculate the offset, set the index count, calculate the size, upload the data range, as was done with the vertex buffer. Again, we have a to-do here about a free list, and then we just move the offset, okay? Next, we update our generation. So if it was invalid ID, then this is the first time it's loaded. We set that to 0. Otherwise, we go ahead and just increment it. if it's a re-upload, then we go ahead and free the vertex data, right? And this is that sort of stub that I have because we don't have a free list yet, right? So we can call something to free this list, but we have no free list to actually add this data to. But at least we have it hooked up here so that later when we do add a free list, all we have to do is add it within this free data range method, okay? And then again, so this is for vertex data, this is for the index data if applicable. So again, if we have index data, we go ahead and call it on there. If not, we don't bother. And then finally, we return true. So that is all of the logic to create the geometry from the renderer perspective. Thankfully, the destruction of the geometry is much more simple. So we check to see if we have geometry, and we check that the internal ID of that geometry is not invalid. We go ahead and use VK device wait idle to make sure that nothing is actually using it. This is probably overkill since this is in a buffer, but I like to do it just in case. The internal data, we go ahead and get a pointer for that. So just as we did above, we free the vertex data, we free the index data if it applies. We go ahead and zero out the internal data, right? And then we set the ID and generation back to invalid ID. And that is destruction. Last piece of this is our renderer draw geometry. And this is mostly the way it needs to be, but we're going to enhance this in a couple of places, right? So we're going to first off make this a little bit more error proof. So first we'll make sure that we actually have geometry to render, and that internal ID of that geometry is not invalid ID. If either of those are true, it just does nothing, okay? Next, we're going to go ahead and grab a pointer to the buffer data, right? Because we actually want the Vulkan geometry buffer data to actually draw, right? So we need to retrieve that from our geometries sub data.geometry internal ID, right? So we go grab a pointer to that. We have our command buffer as normal. Technically, our shader use should probably come first. I'm actually not thinking that we need to do this. We should probably have a check to see if that's needed. I'm just going to put a to-do in there for right now. We should probably just check to see, what the current shader is, and if we actually need to switch to it by calling this use. But for right now, we only have one shader, so it's kind of pointless to check this. But I'm going to put a to-do in there so we don't lose track of it. Okay, so before we had this call to update object, which obviously no longer applies. So we're actually going to want to first call Vulkan material shader set model, passing through the data.model. Okay, and I'm actually going to get rid of this to do because this is no longer temporary code. So let's just get rid of that. Right, and then if we have a material, we're going to go ahead and apply the material, right? So we're going to do that by calling Vulkan material shader apply material. Now it's a bit of an unknown. If we don't have a material here, we should probably apply the default material. In fact, yeah, let's go ahead and do that. Right, so in fact, I'm actually going to set this up a little bit differently. Let's actually take this, move it after this, and we'll create a pointer here called material. We'll just call it M, and we'll set that to 0. And M, oops. So if the data geometry material exists, we'll set M to that. Okay. Otherwise, we will set M to material Do we not have, I don't think we have the, yeah, we don't, so we need the material system here. So we'll include systems, material system, go back down here, material system, get default, right? And we'll just get the default material. And then instead of passing this, we'll just pass M, right? That makes this a little bit more robust. So we'll go ahead and apply the whatever material we have and can use. So if the geometry for some reason doesn't have a material, we can fall back to the default. Okay, so our offsets right now is hard-coded to 0, which is obviously not going to fly anymore. However, we have our buffer data up here. So we're just going to set that to buffer data vertex buffer offset. And down here, this is where we're going to make a little bit of an enhancement. So right now we're assuming that all of our geometry is always going to be indexed, which in most cases it actually will be. But we don't necessarily want to make that assumption anymore, right? So we're actually going to put a check here to say if the buffer data index count is greater than 0, then we're going to go ahead and do this as normal. Otherwise, instead of binding an index buffer and calling command draw indexed, we'll just call command draw, okay? So if I format this a little bit, so what we're really saying here is if we have index data, then we're going to bind the index buffer. And right now, this is actually using an offset of 0, which is wrong. So we need to change that to buffer data index buffer offset, okay? And once we do that, then we call vk command draw indexed. And this is actually making some assumptions as well, which is also wrong. So we actually need to replace this 6 with buffer data index count. Okay, and all the other properties are fine for now. So this is how we draw index data. This is how we draw non-index data, right? And instead we just use the buffer data vertex count to tell us how many vertices we need, okay? And that should be it for that. So I believe that's all of our renderer work that actually needs to be done. The only thing I think we have left to do is, let's see, we have something here in front end that is bleating. Yes, okay. So we have to refactor the way that our render packet works. And we've actually already adjusted the structure of that to take a geometry count and an array of geometries. So actually all we need to do is just adjust this to, instead of using all this hard-coded stuff, to just use what we're passed, right? So what we're going to do is I'm going to take all of this code, everything basically between update global state and end frame, and I'm going to clobber it, right? Because we don't need it anymore. And it's actually going to be replaced by this little snippet. So all we're going to do is obtain the geometry count, loop through every geometry, and call backend draw geometry, passing the geometry itself, right? Couldn't be any simpler, right? And this is why all of this refactoring is needed, is because we don't need to have a complicated front end here, right? As long as we set up all the data the way that we need it, the code becomes very simple like this, okay? So there are a couple of other things that we need to go ahead and address as well. We have some temporary test code in here. So first off, we have this onDebug event. So we no longer actually need this because we're going to move this to the application layer. So I'm going to get rid of that for now. Okay, and I'm also going to get rid of this test material because we don't need that anymore in here, right? And I'm also going to get rid of the event registration. And then during shutdown, I'm going to get rid of the unregistration, right? And that's just going to, clean this up a lot, right? So now our renderer front end only deals with actually rendering stuff. It doesn't deal with creating geometry or anything like that within its initialization. All that's going to be offloaded to the application. Okay, So that fixes our front end. Let's head over to core application. And thankfully this is only, there's only some changes that are actually needed in the C file. So we're going to start all the way at the top, and the first thing that we're going to need is an include for string, because we're going to use some of our string methods. And we're going to go ahead and add our geometry system, and then we're also going to use the math library, at least temporarily. This may or may not wind up being temporary. We may wind up having to have this here for other things. But for right now, I'm going to mark it in temp flags, basically just to not lose track of it. Okay. All right, so next in our application state, we actually need to add two things. So we need to add a field for our memory requirement for our geometry system, and a block of memory to hold the state. And then we're actually going to add a temporary test geometry, and this is where we're going to hold this for now. Again, this doesn't belong in the application. It's technically more of a game or even a scene level type thing where this stuff should be stored. But since we don't have any of that really yet, this is the best place to put it for now. So here is our test geometry. And then what I'm going to do is right below these event handlers, I'm going to add another event handler, which is the one that we snipped out of the renderer front end, right? So this is the one that is hooked up to our debug event that takes in our that changes our texture for a given geometry. And I've made some changes here to basically look at the material in test geometry and directly modify it instead of a test material, right? So it just looks at that if that actually exists, okay? And otherwise, it's pretty much exactly the same, right? So that is that event. That is that event handler, rather. And then in application create, down here with the event registration, I'm going to register a temporary event. This is our event code debug 0, so it's going to be here instead. Okay, and then a little bit further down, right after where we're doing our material system, but before the game, we're going to set up our geometry system. So I set up a configuration here that has a max geometry count of 4096. That can be tweaked. We call initialize to get the memory requirements. We go ahead and allocate our memory. Then we call initialization for real and check it to make sure that it was successful. Bleat about it if not, and return false. Otherwise, we continue. Okay. So geometry system setup looks like just like a lot of the other system setup, right? It's pretty straightforward stuff. Okay, and what we're going to do is we're going to put in some more temp code here. So I want to add these flags, right? And the very first thing that we're going to do is we're going to load up some default geometry. Okay, and that's basically going to set test geometry to get the system default. Okay, and that will be available because we've just initialized this system here. Okay, so we're going to start off with that. We're also going to put some test code into our game loop. So again, we still have to refactor this packet creation, but we are actually going to make this a little bit more robust. So right before we call render a draw frame, we're going to add some packet data, right? So we're going to create a geometry render test data called test render. We're going to set the geometry to our test geometry. We're going to just generate an identity matrix for the model. We can always spin that or make it do whatever it needs to do another time. We'll set our geometry count to 1, and then we'll just fake an array here by passing it the address of test render, right? And then that packet goes ahead and gets sent to draw frame. Okay. And last but not least, we need to make sure that we clean up some stuff. So when we go after the loop here, when we're doing our event unregisters, we need to unregister for that debug event. So that, of course, is wrapped in temporary to-do flags. And then before our material system shutdown, we need to do geometry system shutdown. Okay. And I do believe that is everything that we need to do, at least for right now. So let's go ahead and build. Okay, and we'll go ahead and run. All right, you see we didn't get any validation errors, and here we're looking at our default geometry, right? So we can still swap out our textures, all that still works, right? It's just now we're dealing with a lot cleaner of a setup, okay? So one more thing that I want to sort of display is we're just using test geometry, and that's all well and good, but it doesn't really show off some of the fancy new code that we just wrote, right? So I'm going to go, let's see. So I'm going to go here to where we're loading up our default geometry, and I'm going to comment this out. And I'm going to load up some plane configuration geometry and use our new code for that instead. So, oops. So we're going to load up a plane configuration and then load the geometry from that. So here we are creating a temporary geometry config called gconfig. We are generating a plane config. So we have a width and a height of 10. We have segment counts of 5 in each direction. We are setting the tile to 2.0. So we should see our tile, our textures tile twice in both axes. And then our name is just going to be test geometry, and our material name is test_material, which, if you recall, is our material here, okay? So this should trigger our test material to actually load, right? So when we go ahead and acquire this from config, that should cause a chain reaction to obtain the test material and obtain the proper map as well. Which is paving, right? So we should start off with seeing paving available, okay? So after we do that, if you recall our note here, that vertex and index arrays are dynamically allocated and should be freed upon object disposal, okay? We're going to go ahead and take care of that. So we'll free the vertices and indices, just doing a size calculation for each here, and with the memory tag array, which they were both created with. Okay, so let's go ahead and build this. And what we should wind up with is something that looks remarkably similar to what we had before. Except it isn't. And this is actually kind of what I expect. So if we look at our log here, we see that we failed to load cobblestone 1 PNG because it doesn't exist. So it was unable to load that, and it used the default, which we actually see here. And we see that we have a plane of geometry. We see also that it's a lot more tightly visible in terms of we see also that the texture is a lot more dense because of the tiling. So we know that that's working. It'll be easier here to see in a second. So let's go ahead and fix our material. So I'm going to go ahead and take a look in here. It looks like we've already set this to paving, so I'm just going to guess that the one that is in bin is probably wrong. So we'll take a look at that, and yeah, it's cobblestone 1. So if we do a run task post build, now we see that that's updated, and now we should be good. So we'll go ahead and run again and scroll this all the way down. And now we see that our paving texture has loaded. And we can see that our tiling is working. So, you know, this is relatively the same size as it was. So just to prove that all this kind of works, let's go ahead and let's go back to application. And we will change this to 5 in one direction, right? So we'll make it half as tall as it is wide. And we'll change the tiling to be, let's say, 5 in the X direction, right? And so we should see some really stretched and squashed textures here, right? Which is actually kind of what we expect. So let's go ahead and run this. And now we see basically what we expect, right? we see that the texture is kind of squished in the up and down direction and tiled twice neatly in the up and in the horizontal direction, right? And so with this, we can generate all kinds of test geometry to be able to test out multiple features later down the road, okay? And that is pretty much going to tie it up for this video. So this one, again, has been a little bit of a long video, not as long as the previous two, but you know, we had a lot of ground to cover. So this is the geometry system. Next, we're probably going to take a look at either setting up a static mesh system or potentially maybe our free lists, or we might even switch gears and take a look at resource loaders, right? Because that's going to become an issue sooner rather than later, because one of the things that I want to be able to set up sometime soon is to be able to load up an OBJ file. And to do that, we are going to need both static meshes and our resource system, because I really don't want to write all of that OBJ loading code within the static mesh system. So with that, thank you guys so much for watching. I hope you guys are enjoying this series and learning a lot from it. It's been a lot of fun for me to work on as well. So I hope you guys are enjoying it. If you are, please give it a thumbs up. If you haven't already, consider subscribing. Click the little bell notification icon there to get notifications as to when new videos in this or other series drop. And I will see you guys next time.